Hi everyone, this is part 2 of the forces at an angle video, so please make sure that you've seen part 1 before proceeding. Okay, so to recap the last video, how to resolve vectors into their x and y components, here are a few steps to get you started. You want to sketch the situation and choose your system and add a coordinate grid. So for this example here, our system can be the dog, and I see that I have this blue vector at an angle here. So what I'm going to do is I'm going to add in a y-axis and an x-axis. Looks like this blue vector is at an angle theta to the horizontal. I can sketch in what my x and y components will be. I'm going to call this vector at an angle here f. Okay, this would be its y component, and this would be its x component here. Here's our right angle. We want to always try to identify the angle between our x-axis and the vector we're trying to resolve. Because if we know that, in this case I've labeled it theta, then we can find the x component by taking the vector we're trying to resolve times the cosine of that angle, and we can find our y component by taking the vector we're trying to resolve times the sine of that angle. Okay, so let's try some examples here of determining the components of each vector given. So we've got three diagrams, A, B, and C. The vector at an angle is a 100 Newton force. And if I want to find the x component and the y component for each. Okay, well, my x component here is simply f cosine theta, which means that my x component is 100 newtons times the cosine of 30 degrees. My y component is going to be f sine theta. So my y component in diagram A is just 100 newtons times the sine of 30 degrees. So I find my x component for diagram A to be about 87 newtons and my y component to be about 50 newtons. So I'm just going to add these into the diagram. This one's about 50 newtons. And now I can do the same thing for the 100 Newton vector at a 45 degree angle. And I can repeat that same process for the 100 Newton vector at a 60 degree angle. Here's what happens. We can use the same math model to find the x and y components for diagram B and for diagram C. So I've started you off here for B, again using that same math model, f cosine theta for your x component. And same thing over here, we'll have our f, which is 100 newtons, but now the angle is 60 degrees. So press pause on your video and see if you can find the x and y components for diagrams B and C. Okay, let's check your answers here. We found this x component together for diagram A here. We have our 87 newtons. X component for diagram B, when we increase that angle to 45 degrees, is 71 newtons. And our x component for our 60 degree angle is 50 newtons. Notice as you increase the angle theta, so as you increase the angle between the x-axis and the vector you're trying to resolve, your actual magnitude of your x component decreases. Now let's check out the y components. When theta was 30 degrees, the y component is 50 newtons. At 45, it's 71 newtons. And at 60, it's 87 newtons. So as this angle between the x-axis and the vector you're trying to resolve increases, your y component increases. So now I just have a slide here in words talking about this pattern that we've just discussed here. that as the angle between the x-axis and the vector you're trying to resolve increases, your horizontal component will decrease and your vertical component will increase. And that does make intuitive sense. I mean, if you were to, and I hope nobody does this picture of the dog, I know is a little alarming here, this first picture. If you were to lift the dog up completely in the vertical, which you should never do, but if a person were to do that, then the entire force is exerted in the y direction and your x component is 0. Similarly, if somebody were to pull the dog completely in the horizontal, then all of that force is being exerted in the x direction and your y component is 0. Okay, let's get back to this original problem here and see what we can do. Okay, so let's see what we can do with this problem now that we know how to deal with forces at an angle. So just to recap, Aaron's pulling this system of a sled and some kids, and the total mass of that system is 50 kilograms. He exerts a force of 80 newtons at an angle of 50 degrees above the horizontal. And assuming that friction is negligible here, let's see if we can find the acceleration of the sled. Okay, so even though I have a force at an angle here, the expert problem-solving strategy still remains the same. So the first thing I'm going to do is I'm going to start by drawing a force diagram for the system. And my system in this case is going to be the sled and the children. And I actually have the mass of the sled and the children, so that's a convenient system to choose. The next thing I'm going to do is I'm going to add an x and a y-axis here. So here's my x-axis and here's my y-axis. Okay, so let's start in with a force diagram. The first thing I know is I definitely know the force of Earth on the system here. So that'll be mg here. And if the mass is 50 kilograms, then using an acceleration due to gravity of 10 meters per second squared downward, I can find this weight force, and it would be negative 500 newtons. So I'm going to make my downward direction negative, my upward positive. I'm going to do my right as positive and the left as negative. Okay, I also know that I've got the force of the rope on the sled, and that's given in the problem as 80 newtons. And I know that this actually is at an angle of 50 degrees to my x-axis, so I'll add that in here. Another thing that I know is I know that the ground exerts a force upward on the sled and the children. I don't really know how big to make that vector, but I do know that whatever that normal force is, it's going to be less than 500. And the reason why I know that is because I know that the force of rope on the sled has some y component to it. Okay, now when I think about what I want to do next, I really want to resolve this force of rope on sled so that I can draw a new and improved force diagram. So let me start again with an x and y axis here. Okay, so I'm simply just redrawing the x and y axis that I have so that I can draw a new and improved force diagram where this vector at an angle is resolved and everything that I have will exist on the x and y axis. The reason why I want to do that is because I want to be able to apply Newton's second law in the y direction and then apply Newton's second law in the x direction. And I can't do that if I have these vectors at an angle. So what I'm going to do now is I'm going to add in the forces that I have that are already okay. They already exist exactly on an axis. And then I'm going to resolve that force that's not okay, this force of rope on the sled, into its x and y components. Okay, so to start, we know that mg is negative 500 newtons, the force of Earth on the object, and that's directly on our y-axis, so that one's good to go. I don't know how much the normal force is, but I do know that whatever it is, it's less than 500 newtons. So I'm going to add in the normal force, but I'm not really sure yet how big it is in terms of magnitude. I'm just going to draw the vector shorter than I drew for the weight force. But again, I'm just not quite sure how much that is yet, so I'm going to leave that as a question mark. I do know that there will be some y component to the force of the rope on the sled. And I know that I would be able to find that because this is going to be F times sine of theta. So this is going to be easily found if I do the y component equals F times the sine of the angle between the vector I'm trying to resolve and the x-axis. So this one becomes the y component equals 80 newtons times the sine of 50 degrees. And that comes out to about 61 newtons. So now I can add that into my force diagram that the y component is 61 newtons. Okay, so we're going to find the x component in the same way. I can draw this in, and it would be represented by F cosine theta. And so we can figure that one out. F cosine theta is our x component. So that means that our x component is just 80 newtons times the cosine of 50 degrees. And that gets us about 51 newtons for that one. Okay, so I'm going to add that into our force diagram. And looking at the force diagram, just thinking about this situation, I know that acceleration in the y direction is 0 meters per second squared, right? If he's pulling the sled in the x direction here, and you've ever been on a sled before, then you know that the acceleration in the y direction is most likely 0. So this means that the net force in the y direction is going to be 0 newtons. And that allows me to write a net force statement for the y forces, and that'll be mg plus F sine theta, which we found, plus this unknown normal force. Okay, so let's see what we can find here. mg is going to be negative 500 newtons. F sine theta we found is positive 61 newtons. That leaves us with our unknown normal force. This makes this negative 439 newtons plus the normal force. And so if we add that negative 439 to both sides, we end up with a normal force that's equal to 439 newtons. So now this unknown is now a known. Now when I look at acceleration in the x direction, I can't say that it's 0 because I have a net force in the x direction, and it happens to be to the right. And when looking at the force diagram here, I can tell that there are no forces to the left here. So that means that my net force is simply F cosine theta, or the x component of the force of rope on the sled. Okay, so this means that my net force is equal to 51 newtons. Now I can find acceleration in the x direction because I have F net in the x direction, and I was given the mass of the system. So my acceleration in the x direction will be 51 newtons divided by the 50 kilograms that represents the mass of the system. And if I just take my 51 here divided by 50, come out with an acceleration of 1.02. So about 1 meter per second squared. I hope that you found this tutorial useful, and it gives you a good starter example here for how to deal with forces at an angle. If you have any questions, let me know, and I hope you have a great day.